click. And then, yeah. Harmonics flow in power network part 2. This one is no longer needed. As a result, I will have nice set of lectures. Is there any chance someone arrive?
Abdur said that he should come at 12:30.
Maybe comes, maybe not. Wait. Not. Okay, we can start.
Yeah. He wrote that he will have some questions, so when he'll come, right now it's gonna be recorded, so.
Okay. Okay. No, it's not our. What I have for today? My blackboard. Today I want to speak about harmonics flow in power network and take another key network element, transformer. What's going on with transformer? transformer. 1, 3. 1 against voltage, 1 against and against V1. It's what we know. Transformers are necessary because when we need to transfer energy, usually energy is not produced at a consumption point. To transfer energy we need higher voltage because it allows us to reduce losses. But consume energy at high voltage, a bit unpractical. It's dangerous, so we need to rise voltage at the generation point and then lower it at consumption point. And better not to lose much of energy. But here we speak on signals theory. I have prepared a small demo. I have small transformer at the primary winding. I have a voltage source and I took small resistance, like 10 ohms. It's not important. I have resistor here and I took voltage. So S1 is magnetizing current multiplied by F1. Or something K1 ash, because we also know number of turns at a primary winding. Secondary winding, I work with network of resistor and condenser. This is, and I specially selected a much higher when capacitor resistance. Voltage A is 1 against capacitance, integrating from 0 to time. Capacitor current. It's clear. EMF of the secondary winding will be I need to clear some space. As a function of time, it will be minus flux, and it will be number of turns multiplied by first derivative of the flux. Yeah? Yeah. But current, this current, is virtual divided by R2 because this resistance is much higher than any other resistance in the network. So integrating derivative, what I get?
The flux.
Yes. And being minus v2 divided by f integrate from 0 to time. Scale factor, induction of flux as a function of time. So, if I create a research figure S1 and at Y S2, what I'll get? I'll get chart where here I'll have magnetizing force as a function of time and an equal flux or induction. Flux. Let's see what I'm getting. I should come closer to make it visible. Here it is, the magnetizing chart of my small transformer. And yellow line, magnetizing current as a function of time. I can also, what I can do, let's take the red one. The red wire. Okay. Oh. Here it is. The secondary voltage. The yellow line primary current and the blue line secondary voltage. And like this. And hysteresis, cool or magnetizing charge. Primary current multiplied by winding or magnetic magnetic moving force and vertical induction. Symmetric should be. Now we see unloaded transformer. 1 second, I'll take the load resistance. Okay. Let's see. Load. What happens under load? Load. It was not unloaded transformer. I'm increasing the load. Now we have a short circuit regime. At a short circuit regime, with higher voltage. In a short circuit, no load regime, normal load, transformer overloaded, short circuit. At a short circuit regime, and the induction is half of the normal. Okay. I'll take back my scope. We saw load regime. There is one moment. I have a sine, network voltage, sine. Output, we can say it's a sine. But why current is not sine?
Eddy currents?
Yeah. Why current? It's a primary current. It definitely contains higher harmonics. We need to take a look on transformers. I'll draw a diagram. Diagram will be drawn. I'll switch to my board. I'll fill this space. It's a large time scale. Where we start from? Transformer is connected to the mains with voltage something like, let's say its mains. This is sine omega t. 50 Hz voltage from the transformer. What happens? I have connected transformer to the network. Magnetizing current flows, no load regime. Magnetizing current flows and inducts a self-induction EMF in a primary winding. And this self-induction EMF is in equilibrium with the primary voltage. It's equal to primary voltage. I should draw a mirror line. Self EMF. It's an EMF on transformer primary winding. Should I bring a large transformer? Transformer. understand here. If I attach 220 volts here, primary current flows, induction and flux appear, and self-induction EMF is equal to the mains voltage but with minus sign. They are in equilibrium. But what we know about this? What it is minus number of turns in primary winding and a first derivative of the flux. What should be a flux to make such red line? Derivative of the sine is cosine, isn't it? If we want to know the flux, we should take an integral of this, of red line. Huh? And integrating, this is if this one is sine of omega t, red one is minus sine of omega. Integral of minus sine is cosine. Okay? So this means that flux cosine omega t. This is the green line is flux. Nice. And now why I left this space? I have this space for my nice green chart. I want to have a magnetizing curve here. Bit too high. One second. Should be symmetric. Oh, something like this. Okay, let it be something like this. Here I have a magnetizing curve, this one. Bit in different scale, okay, it's not problem. So, let's take one moment of time. We have this one is up, this one is down. We will go down, so this should be this point. Now, I will have a time scale here, and this will be my primary current. The first point at 0 time here. Next one, this one will be T1 and T1 here, and here is my point. T2, T2, and so on. Okay, this one, let's say it's T3, at a 0 I'll have a max, and so on. Idea is clear. As a result, when it goes straight and then something like this, and it will draw peaks. I don't have a space. Anyway, idea of design is clear. We will get, I know what we will get. We will get this. As a result, this chart will create something we see. What's the idea behind? We have sine voltage, mains voltage. We have sine output. But because steel of transformer has this magnetizing characteristic, magnetizing looks like this. It's not an ideal straight line. We will get such kind of magnetizing primary current, and this current contains third and fifth harmonics. One moment, I'll order. Come on, yeah. See it here. Take a look. 1 second, and first point 50 Hertz, and second visible 150 Hertz, third harmonic. If I increase voltage, I'm going far into saturation area. What we can see? Huge rise, but mostly in third harmonic. And now distortion in the secondary voltage, because I'm overusing the core. Something like this will be okay. And now question, what it will be if primary current would not contain third harmonic? I made this circuit. It's a resonant counter for 150 Hertz. It will reduce it will increase resistance at a frequency of 150 Hertz 3 times. Let's see what happened. Only one question. 1 second, I need a red light. Transformer can go. I'll put in series with the primary winding. This one. Resonant counter. You see, I have reduced this part. Now, there's increased resistance at 150 Hertz. And look what happened with the secondary voltage. Why? See what happens. I have increased resistance at a third harmonic frequency. Now, magnetizing current contains less third harmonic. Yeah, this way better. See, it's not distorted. It's much more like sine with switched resonant frequency. Now, what happened? Flux, if I reduce artificial amount of third harmonics in the magnetizing current, flux will not contain components related to third harmonics. It's like apply to this nice green flux additional minus third, like it's orange. It's minus sine. 1 second, the period of flux is somewhere here. This should be something like this. It's a flux at a free omega. And flux will have distortions. Now flux is not cosine. And these distortions appears in secondary voltage. Very loudly. You can see it. It's clearly third harmonics. If we remove wait. Kom, zvani. Man tagad lekcija, es pēc lekcijas palikšu. Jā, būs ok. Okay, so if we remove third harmonic from the flux, not remove but apply minus third harmonic to the flux, we will see distortions of the secondary voltage. And why we apply this inverted third harmonic? Because primary current do not contain third harmonic is as it should be. Of course, it's a nice question. Why should someone do this? Why should someone apply this filter or do something like this? I did it for illustration. At this moment, my network is single phase. But what about three phase networks? What about polyphase network? So we have idea. Say we have separate transformer for the each phase. This is A phase, B and C phase. Neutral. We have an Y connection. Here we have A point is current, B and C currents. We can draw at 50 Hertz A, B, C. Each current here contains first harmonic and third harmonic. So we have both 50 and 150 Hertz. For 50 Hertz we have star. So current, neutral current, what will be? A plus B plus C equals to 0. At 50 Hertz, sum equals to 0. But what will be with the third harmonic? Network voltage 50 Hertz. But current should contain not only 50 Hertz component, but also 150. Or you can see this distortion. At 150 Hertz or at triple network frequency, we have a 0 seconds. And current should be triple. So theory says what here we will see triple third harmonic current. It's strange. And definitely we need to test it. Is it true or not? I'll use controllable voltage source. I'll use. Okay. It's source installed. And where are you? Yes. And I will use the small power transformer to analyze what's going on. Come on. This will be secondary voltage. I'll have resistance in the neutral, and this will be my first signal. And this will be my second signal. What can I do? Just to zero and disconnect. I don't need this one, but I'll need close it. 1 second, where is my wire? 1 second, I'll connect components. Hey, transformer. Don't move. This one goes here, this goes here, red to the red, black to the black, And. Second, I'll bring scope. Okay, I'll set 200 volt start of 200 volts. Yeah. One moment. What we got here? 3 lines. This one, secondary voltage. Sine with voltage with frequency of 50 Hz. This one is neutral current. And you can see it's 150 Hz. It's pure third harmonic. Transformer. Now it's unloaded. I have put load on. Voltage decreases, but neutral current. This neutral current remains unchanged because it contains of the pure third harmonic. It's a third harmonic component of the magnetizing current. Now let's try to increase voltage. I'll increase to 220 volts. It's a nominal for this transformer. What was the value of yellow line? 119, 190 millivolts. Okay, now I have 220 prepared. We see increase 188. Third, we see just load is symmetric, and we have little pure third harmonic as a neutral current. 189. Remember this 1 and 9. Now I'll increase voltage to 230 volts. Three 360. I have added only 20 volts. It's less than 10%. And we see just doubling in the amplitude of the third harmonic. We are going to into saturation. Also, and now, question for million. What will happen if I disconnect the neutral wire? Now we see third harmonic flowing through the neutral. If I disconnect it, can third harmonic flow? No. And we will see the same situation what I modeled with my coil. Look. You can see distortions in the secondary voltage. Right? It's a bit slow in reaction, but you can see more amplitude increase, and it's like more sharper shape. let's make it more visible. I'll change voltage to 250. For a short time. .486 amplitude, and look what happens with the secondary voltage. See? And now for comparison, I'll switch back to 220 to the nominal scale. .188 current, netto current, and a very small change in secondary voltage when netto is disconnected. We saw one of the effects of distribution network. 10 kilowatt network, by base operates with isolated neutral. When cheaper transformer Y0 connected to this network, when voltage is near nominal, everything fine, we saw nothing special happens. But at night, when network is not loaded, if voltage control system is not working well, voltage rises, amount of third harmonic in the magnetized current rises, and we will see over voltage. Another influence or mitigating factor is what loaded transformer. We saw load current reduce induction in the transformer core. At night, daytime transformers are loaded, so induction do not reach this end, this end zone of saturation. At night, when there are no load, transformer core saturates large amount of third harmonic in the neutral current, but neutral is isolated, so we'll see over voltage. It's one of the possible problems of distribution networks. What can we do? Use a delta connection. Here we have star or Y connection. More preferable to use not a star but delta. Something like this. This will be the kilovolts part. For the 50 Hz, in such connection, what will happen? We again see A plus B plus E equals to 0 at 50 Hz. For third harmonic, delta connection is short circuit. Short circuit. We'll see triple third harmonic EMF divided by sum of this resistance. Third harmonic will circulate in the delta connection. It's like short circuit. And what will happen? We don't have neutral here. At the first approach, third harmonic should not appear, and we will see flux of the third harmonic with the minus sign. But at the moment it arrives, we will have induced third harmonic here, and inducing short circuit. And circulating current of the third harmonic will produce one more flux in the needed direction. So as a result, these two third harmonic flux are compensates. It's theory. In reality, we will have cosine flux in the core. For delta connection, third harmonic, for the third harmonic, delta connection is short circuit. And circulating third harmonic current will compensate all disturbance. So we will have no problem with the voltage quality at the client side. Such transformers are roughly 1.78 times, 1.7 times expensive when the grounded wire are less expensive. They're cheap, honestly. But they produce disturbed voltage. Very old regulations allowed such transformer in the city networks for rated powers up to 1.5 megavolt amperes. Now I'm not. They are city networks are allowed to keep them keep installed, but as a new installation of new such transformer is not recommended. You can keep old transformer if you already installed it. Delta connection must preferable. Must be preferred, or is more preferable, because it ensures better voltage quality, and there is no possibility of overvoltage due to core separation. In our case, what we saw due to lack of the third harmonic flow. So, conclusion, power transformer with a steel core is a natural source of the third harmonic. And flow of the third harmonic determines say performance of, or not through this term, but is an important factor in performance of the distribution network. While phase currents are formed mostly by 50 Hz component, neutral current, in our case, is shaped by the third harmonic, by the 150 Hz component. That's what I have for today.